discussed this morning. Not so much detail, but you're going to hear more about it. And the nice thing about it is, well, there are several nice things about it. First of all, as you're going to hear, you can get a statistical population of states with this reaction. The nucleus also recoils, but if I wanted to discuss this in terms of the energy levels involved, we of course start with the nucleus in its ground state. We excite it to, oops, it wasn't supposed to go away. We excite it and then it decays to another state, or eventually you're going to end up at the ground state. Now, purposely those decays were of different lifetimes. I think you saw one of them was kind of slow, the other one's kind of fast. It's important we be able to determine that, just how fast those decays are. Now the neutrons we use are produced by either of two reactions. We can use the PN reaction on tritium to give us helium-3. The Q value is minus 1 MeV. Or we can use the DN reaction on deuterium. Both in cases we end up with helium-3 as a residual nucleus. And the Q value in this case is plus 3 MeV. Now the accelerator voltages we have available are in this range typically. And if we use this first reaction with these energies, then we get neutrons that are from about half an MeV up to 6 MeV. With the second reaction, we can get neutrons that are about 4.5 to 10 MeV. So you can see we have continuously variable neutron energies from half an MeV up to 10 MeV. There are other reactions we can go to higher energies, but those get to be a little bit uncivilized. So let me, again, illustrate how we produce our neutrons. This is our proton coming in, produces a neutron, which then scatters from our target nucleus. Neutron is emitted, and then gamma rays follow. Okay, this illustrates schematically again how we do it, but with a little bit more realistic drawing of how we would detect the gamma rays from the scattering. The beam comes in, the neutrons strike our scattering sample, and we detect them in a detector. It's about a meter away. Now, you can see that there's a large amount of shielding here of various descriptions. There's tungsten shielding, copper shielding, various other kinds of shielding. Our detector is back here. It's surrounded by a bismuth germanate Danny Compton shield. We do what we can, of course, to shield the detector from the incident neutrons that are produced. This is just a photograph or a series of photographs of the laboratory. The beam comes in here. Our gas cell is there, scattering sample, detector. This is another view. Beam comes in. There's the gas cell, scattering sample. This is our gas handling system. One of the gases we handle is tritium gas. And tritium, as you know, is radioactive. It's not extremely hazardous, but it is still radioactive. We handle that very safely, and we have for a large number of years. It's very important to our program. Again, these are just other views: scattering sample, gas cell, detector. Okay, and this is the kind of data that we would get typically. Now, this shows 3 MeV neutrons incident on cadmium-114 enriched target, and to nuclear spectroscopists, this is a beautiful spectrum. To many of you, it looks a little complex. We can control the complexity of that spectrum. If we were to lower the energy of the incident neutrons from 3 MeV down to 1 MeV, everything in that spectrum would disappear except for this one line. Why is that? It's just energy conservation. You can only put so much energy in with a 1 MeV neutron. There's only one excited state below 1 MeV. That's all you populate. This kind of shows you in a little bit more detail. The spectra are very nice. Again, this is Compton suppressed with time of flight gating, various things we can do to reduce the backgrounds. I'm going to focus on this little gamma ray here, because if I were to plot the yield of that gamma ray as a function of incident neutron energy, I would get something that looks like this. You can see that below about 2.9 MeV, we don't have anything. So this tells you that the emitting state, or the energy of that level, is be about 2.9 MeV. And we can do this for a number of levels in the nucleus. We simply plot the energy of the gamma ray as a function of incident neutron energy. We get these so-called excitation functions, as you heard about earlier this morning. And you can see that when we compare these with statistical model calculations, the agreements are generally quite good with what we believe, or what we from this method or other methods can determine the spin to be. This is perhaps the worst in the agreement. We don't know why, but occasionally they don't agree quite as well as we would like. We can also measure the angular distribution of the emitted radiations, and we have this Legendre polynomial term which describes the angular distribution. We compare these angular distributions with statistical model calculations. Actually, a fairly old statistical model seems to work very well for us. And from these, we can determine something about the spin. We can measure multiple mixing ratios. Now, multiple mixing ratios typically means we're determining the M1 and E2 components of a particular decay. And this one I'd like to show, we just measured this recently. We didn't make a special effort to measure it, but we did have to do wanted to do some other measurements on iron 56. It turns out that this is a particularly well-known mixing, this transition has a particularly well-known mixing ratio, and that's shown over here. The NMDC, or the accepted value, is shown here. Our value is shown there. And we can effectively measure mixing ratios, and I think we do it about as well as anyone can do it. Mixing ratios, and for those experts in the audience, are sometimes difficult things to measure. You measured a lot of them, John. Did you always get them right?
92%.
92%. That's better than most. We can also do coincidence measurements. We take 4 detectors. These are not Compton suppressed detectors in this particular case, because in neutron scattering you try to minimize the amount of mass that you have. And when you put Compton shields near your detectors, these provide more mass, more background. So these are bare germanium detectors. And we kind of reverse the geometry to collimate the neutrons as much as you can. So if a neutron comes in, scatters off our scattering sample, and you get events in 2 detectors, and of course you have a coincidence. And that means that those 2 gamma rays, in principle, should have occurred from the same nucleus at the same time. This just shows a little bit more detail how we do this. This is our collimator. You can see the detectors in the back. Beam comes in, there's a gas cell. And this is, actually this is not a typical spectrum. This for us was a fairly small scattering sample of 10, 1, 12. You can see the first 2 excited states, and we gate on this gamma ray, and we look for things that are in coincidence. Well, of course, the 1257 is easily in coincidence, but you can see a number of weaker things there. Where do those arise from? Well, those arise from gamma rays coming in from higher lying states. Okay, now we frequently advertise that we use monoenergetic neutrons. And the question is, how monoenergetic are these? If this is our gas cell, and we've got tritium gas in it, we use protons in and neutrons out. We have a scattering sample shown here. The gamma ray goes off, neutron is scattered there. The question is just how monoenergetic are these neutrons that are incident? Well, this is just a calculation. If we have neutrons at 1.75 MeV, and we have these contributions, so that the spread in energies, when you sum up those contributions, is about 100 keV. That's fairly monoenergetic. You can go to higher energies, and you can see the contributions from these various sources change a little bit, but it's still about that order of magnitude. Okay. So I've told you about inelastic neutron scattering with accelerator-produced neutrons. One big advantage is there's no Coulomb barrier. We have variable neutron energy, so we can come in and excite the nucleus to any degree that we want. Question?
Is the target in air or scattering chamber? Everything is in air.
Excuse me.
No, everything is in air. The
In air.
target is in air.
Air.
No scattering chamber.
No scattering chamber.
See, you don't consider the effect of scattering because there is no scattering chamber. That's very important.
Yes, it is, okay? If you put a scattering chamber near neutrons, that provides lots of mass and that provides background.
But you don't tell the associated particles to detect the neutron energy in other ways.
Yeah, you'd really like to do these experiments in the middle of a football field,
Exactly.
so that the neutrons, after you use them, they just go away.
Exactly.
So we can excite the nucleus to any degree that we want. We have excellent energy resolution.
I think you can lift it
If
up.
I could reach it, I would close it. Rom?
No, but you can lift up. I don't need so much sun.
Well, I think only Andrea can reach there.
Okay. Did you see the screen okay?
Yeah.
Yeah, that's good.
Okay. Again, we have excellent energy resolution since we're detecting gamma rays. We could detect the scattered neutrons, but that's much more difficult. The efficiencies are typically lower, and it's just more difficult. You typically have to use time of flight methods in order to determine the energies. One of the things I didn't say is that this reaction is essentially non-selective. What do I mean by non-selective? I mean statistical. Okay? And you're going to learn more, I think, about statistical model population of states. I took this particular thing out because I want to talk about that tomorrow, the lifetimes we measure. We can measure gamma-gamma coincidences, and there's some references here. We are limited to stable nuclei. Why are we limited to stable nuclei? It's not because the cross-sections are small, they're not. It's because our fluxes are small. Because these are, if you want to say it, radioactive beams. Not radioactive ion beams, but radioactive beams. Neutrons are radioactive. So we have to use stable nuclei. And typically, in order to make things simple, we like to have enriched isotopes. Now, our typical scattering sample might be of the order of 20 or 30 or 40 grams of material. Where do you get that kind of material of enriched isotopes? Well, you can rent it or lease it from Oak Ridge National Laboratory at exorbitant prices, but that's the price of doing business. So we lease these scattering samples, return them unharmed, and everybody's happy. Okay. Are there any questions so far?
Don't you make the sample slightly radioactive in all your neutrons, or doesn't don't say anything to anybody?
As you know, John, if you stay below the separation energy, the neutron separation energy, you don't activate anything. On occasion, we have made mistakes, but they're typically minor. One of the nice things about these scattering samples, or about these our measurements, are our fluxes are small. So if you activate something, you don't activate it very much.
I would have thought you've got a bit of capture, so it depends what you've obviously got in there as a target.
Yeah, we keep hydrogenous materials or light materials away from our setup, so we don't get very much thermal, very many thermal neutrons.
Cross-section goes down.
Yeah.
Energy goes up.
But you're right, you're worrying about all the things that we should be worried about.
Could I maybe ask a question? It's not quite clear to me how you collimate the neutrons, if you collimate them at all. What do you?
That's a good question, David.
How do you control the neutrons?
You don't. You simply make a hole and you let the neutrons that go into the collimator react.
Right. So
You don't really collimate.
So the ones that don't go in the hole go elsewhere, and the ones that go in the hole
Exactly.
you use.
That's exactly right. Is there another question?
Was a technical one. Why you use molybdenum and not other things before the gas targets?
Yeah, the reason we use molybdenum is we understand